Okay guys, so now that we've got our formula, we can start finding some sums using it. I'm actually realizing now that number 2 is the same question as number 1, except for I neglected to actually find that sum. Rest assured it would just, be adding up all our terms from number 1. So using our sum formula, the sum of the first 6 terms, I'm going to say sum of 6, is first term, which is 20, times 1 minus our ratio, which remember that's your common ratio, of 3 to the power of n, remember it's 6 terms, all over 1 minus our ratio of 3. So kind of color coding things, like that's our first term. We've got our common ratio, which is 3 and 3, and then our number of terms is 6, and that's kind of here and here. Okay, so that's the general formula. From there we're going to plug it into our calculator. And I just want to show you guys how to plug it into a calculator because a lot of my students in Algebra 2 Honors will make mistakes as they're first learning this with order of operations. So the first thing you want to calculate is what's in the parentheses, specifically your exponent. So I would first do 3 to the power of 6. And then I would do 1 minus that. So 1 minus, and my calculator, I can call the last answer by doing second, which is the yellow button, and the negative sign has a little ANS for answer above it. So negative 728, and then I have to do all of that times 20, divided by, in parentheses, 1 minus 3, or you could type in a negative 2. So it looks like it's 7280. Okay, and that's how you use the formula. Just make sure when you're using your calculator you're careful about doing the correct order of operations. So number 3 is also asking us to find a sum. It's using some notation that's called sigma notation. And this notation I haven't really seen at all coming up in competition problems. It's just a fancy notation that Algebra 2 uses. What it tells you is to start with the first term, stop at the 5th term. So it's saying sum of the first 5 terms. And your rule, your a sub n rule, is 10 times 1/2 to the n minus 1. So it's basically just a more compact way of telling you that you're finding the sum. So for this one, if I was using my formula, right, I have my formula here. I can plug all those big ideas into the sum formula. I have my first term, I have my ratio. They were telling me to do the first 5 terms. So now that you guys have that context, I want you to try to finish off part A and also do part B. Unpause the video when you're ready to go ahead and check your work. So here's your answer for part A finished out. Part B, you might have gotten a little stuck because they are asking us to do something different, where we're starting with the 7th term and stopping with the 19th term. So it's a little trickier. To give context for how you would go about this, I want you to think about it in the context that your first term would really be like your 7th term, because that's where you are starting. So that part's pretty straightforward once you kind of think through that. And your first term, plugging it into your formula, which remember, here's your rule. So I'm plugging it into my general formula and getting 640 as my 7th term, which is going to count as my first term in the formula. So that's going to be like my a sub 1 will be 640. The tricky thing is the number of terms. And the number of terms, a lot of people will say, okay, it's 19 minus 7 or 12. But I want you to think about if you read pages in a book, you would read 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So it's actually going to be 12 plus 1 or 13 terms. And a lot of students have trouble with this because they think of it as just subtraction. But when you're counting terms, if you just subtract it, like if you do 19 minus 7, you're finding how far apart the 7 and the 19 are, which if you start here, and do however many hops, it's telling you that it's 12 apart, but you have to also take into account where you are starting, that you're including the beginning as well in your list. So I like to think of it that way. You can also think about it as book pages, right? If I told you to read pages 2 through 10, right? You could think about how you would probably say 8, but it's actually 9, because 2, 3, 4, 5, 6, 7, 8, 9, 10. So think about those in the context of why it's that way. Plugging everything in, our sum of our 13 terms is going to be our first term, which is 640, times 1 minus our ratio of 2 to the power of 13, all over 1 minus our ratio of 2. Okay, and I'm just going to pause the video to plug that all in my calculator. Okay, and here is your final answer, all plugged in. Remember to keep in mind order of operations. You want to start with the 2 to the 13th, finish off what's in parentheses, and then keep going from there. There's a couple of interesting word problems to think through here. So I want you to answer this question and give some support. Unpause when you're ready to compare your thoughts and mine. Okay, so the two options are, would you rather get $1 million this month or get a penny today, 2 pennies tomorrow, 4 pennies the next day? And you probably at first are thinking, well, the second option doesn't look very exciting right now. But thinking about the fact that you're doubling every day, it might be able to grow to a substantial amount towards the end. And if you're thinking along those lines, you're correct. This is following a geometric pattern. Your general rule is over here in the box. Your first term is 1 penny. Your common ratio is 2 because you're doubling it every day. And so you've got the first term times your ratio to the power of n minus 1. Plugging everything into your formula. I'm just going to assume, let's say a month is 30 days. Because most months are 30 or 31. So I'm kind of lowballing it just to make sure that we're looking at the lower end of the spectrum to see if it will beat $1 million. And it most definitely does. We get to a sum of about $10.7 million after 30 days of adding all that money together. So kind of a fun real world example. Now this next idea is an infinite sum. So we didn't have an infinite sum for arithmetic, but the question is, could we for geometric? Could we say that we want to keep going to infinity and never stop? So I want you to think about, can an infinite number of terms add to a finite number? Is that possible? And normally what I would do in class to help students get to the concept of an infinite sum is I would do something called the paper challenge. Okay, so here's what the paper challenge normally looks like. You have a group of 3, and one person is the paper master. So let's say that I'm the paper master. So Kayla's going to be paper master, and I've got 2 sisters, Carly and Courtney. Okay, so I'm paper master, so I'm going to have like a little star next to me. So the way that this game works is, for the paper challenge, you are a paper master and you start with a piece of paper. Feel free to do this with siblings at home, parents, guardians, whoever's at home. Feel free to play this game with them and see if they understand the big idea. So paper master is going to take their paper and they're going to cut it into 3 equal pieces. So piece 1, piece 2, piece 3. Courtney's going to get one of them. Carly's going to get one of them. And I'm going to keep the last one to keep ripping it up. So far, each of them have a third of the original sheet. Okay, so what I have left is that size, right? So I'm going to now take that strip of paper and I'm going to cut it into 3 again. And then Courtney's going to get one of these. Carly's going to get one of these. And I'm going to keep one more so that I can keep ripping the paper and continue to give half of my sheet to, or a third of my sheet, excuse me, to each of my sisters. So what previously we had was a third, right? If I do a third cut into 3 equal groups, that's going to be plus a 9th. So they each have a third plus a 9th. I'm going to draw, so this is what I've got left. And I'm gonna keep going. Right, I'm gonna give one of my thirds to Courtney, and give one of my thirds to Carly, and I'm gonna keep one more third left so that I can continue to cut it into 3 equal pieces each time. This last one was a third of a ninth, which is a 27th. So what I want you to imagine is, if I kept going on and on forever, what will these sums, Carly and Courtney's paper that they have, if I keep taking my paper and I keep ripping it into 3 equal pieces, give one, give the other, keep the last one, and keep ripping, what is Carly and Courtney's sums going to eventually get really, really, really close to as I keep doing this infinitely? So what does a third, a ninth, a 27th, and so on get about to as you go infinitely? You've guessed it, it's approximately a half. Because what's happening is Carly and Courtney are getting really close to a half of the original piece of paper, because as I go on and on forever, the amount that I have left that I'm cutting into 3 equal pieces is getting really, really, really teeny tiny as I keep going. So it's kind of an interesting concept, is that as I keep doing that, it's going to get closer and closer to a half. So that's one way that you can think about why it's possible. And then this is the paper challenge that we just talked about. And this is going to come out to, I'm just going to take that away, to about half. And some of my students don't like the equal sign, so some of my students in the past prefer to use an approximation rather than to say it's exactly equal to. Either way is fine. So here's how we can figure out what the infinite sum formula looks like for a geometric series. If I take my geometric series formula, and let's say my number of terms is really, really big, like it's 1,000,000 terms, right? As I get to bigger and bigger numbers, what happens if I do a ratio? Like my ratio might be a third, right? What happens if I do something like a third to the 1,000,000th power? I'm going to do a third to the power of 1,000,000. Now it says it's 0, but really a third to the 1,000,000th power is like a third times a third times a third. So it's really just a really, really tiny fraction. It's not exactly 0, but it gets really close to 0. So the big idea is, as I do the ratio to the nth power, that's getting really, 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 really close to 0. So we can say it's approximately 0. So then what will happen is my formula will become a1, first term, times 1 minus nothing, all over 1 minus the ratio. Well, 1 minus nothing is just a 1, and 1 times a1 is a1. So your formula simplifies to the formula that I've got below here in the box, and this is our infinite sum formula. The only rules that they say here is that your ratio has to be smaller than 1 when you take the absolute value. So that means you could have something like a half, negative 1/2, a third, 4/5, negative 4/5. Basically, all that they're saying is that your ratio can't be a positive or negative number that's, 1 or up, or -1 or down. So for example, over on the side, I've got a couple of examples of sequences. The first one starts at 1 and has a ratio of 1. So I do times 1 every time. If I were to add those up, that sum would just keep growing. It's not going to arrive at a specific concrete answer. The same thing happens for my example below, where I do times 2 every time. Those will just keep growing. They do what we call diverging, which means that they just keep growing and they don't arrive at a specific sum. Okay, so you can think about that idea as you reflect with this question. The connection to the finite formula was just this idea up here that I was showing you guys. And then there's just kind of a putting it all together question as well. So unpause when you're ready to see these two. Okay, your answers. The reflection is just like up above, the sum just keeps growing. Number 1's really interesting, so we'll probably chat about it together.